All right. Oh, go all the way back up. Lesson 20. Okay, so this one's going to be on. Oh, let somebody in. This one's going to be on magnetic forces with charged particles. So this is actually like similar to last time, right? So last time we had charged particles creating these magnetic fields. Now we're almost kind of doing like the flip of this now, where we're going to have an already created magnetic field, and we're going to see what type of effect does that have on a particle traveling through it, right? So let's look at what's going on like in this picture. So they're saying what would happen if this particle, so again, let's do a little bit of review here. This is a particle, let's say it's positively charged, just because I know it is from below there. And so we're looking at an X. So what that means is that particle is traveling into the page, right? That particle is like going into the page right now. These arrows going from left to right there, that's our magnetic field, right? It's going from the north pole of that magnet to the south pole of that magnet. And just something kind of interesting happens here. Actually, really interesting. This is actually a big part of how like motors and everything else are going to work, and lots of like our technology is all based on some of these ideas between the next few lessons we're going to do. But this is what happened, or what happens is that if we've got this charged particle, going into the page, and then we know from the last lesson, if you guys, it'd be good review here. Let's say that this is a positively charged particle. So using your first hand rule, what you do is you'd have your thumb pointing into the page. I know you're all doing this with me right now, right? So thumb pointing into the page, and then your fingers would be curling around, and you should have them curling around going clockwise, right? So in the direction that these arrows are going. So that all makes sense. We've done that. And then what we can do is, if you can imagine that at the top of this, the magnetic field at the top of this thing at this point, right? You can imagine that there was like a little magnet that it created, because, I'm just following the magnetic field here, right? So it's going from, it's like this would be the south pole of the magnet, and that'd be the north pole of the magnet, because the magnet or the compass needle would point in the direction of the magnetic field like that. And on the bottom, you'd have the opposite, right? The north would be going the other way, and the south would be, north would be on that side, south would be on that side. Well, what you can kind of see going on there is that, picture that there's like a tiny little magnet at the top of this, guy. Well, we know that north pole of a magnet attracts the south pole of a magnet. So what we kind of have going on here is that this north pole is kind of like up a little higher. It's going to be pulled back down toward that magnet. And you've got the same thing happening on the other side. You've got this south pole is going to pull this thing down toward the north pole of that magnet, right? So that alone, you can imagine that those were like strings or something, right? If you just pulled those things down, that's going to make this particle move downward, right? So that's pulling it down. But then you've also got the same thing happening on the bottom here, where I know that south and south pole magnets would repel. So the same thing's going to happen. You're going to have these things, like this magnet's going to be like pushing on that one. It's going to be pushing it away. And then the same on that side, that's pushing it away. So all of that being said, the net result that's going to happen here is, if I shoot a charged particle between two magnetic field, like between two magnets like this, so in a magnetic field, what'll end up happening is that the thing will deflect downward. And this is huge. Like this is actually like a really applicable thing that we can use for technology now. And you guys will start showing that this actually shows up quite a lot, like in technology. This is a huge part of the Industrial Revolution, and the world that we live in is based on some of these principles that we're going to go through. Okay, so now we're going to introduce a third hand rule to kind of make a bit more sense of what's going on here now. So here's the third hand rule. So just maybe a recap there. The first hand rule was for when you had, like a charged particle going into the page like that, right? So that'd be right hand for positive, and then you'd have the magnetic field going around that way, right? So that was first hand rule. Second hand rule had to do with the coils, right? That was the solenoid one. So that was if you had, let's say, a charge going this way to that way, and maybe it was like a negative the charge. So it'd be your left hand. So then it's kind of hard to see which way that's wrapping because it's two-dimensional. But in the end, your thumb would be pointing to the north side there, right? If it was like going around the back side, maybe that might be a weird optical illusion. It almost looks like you can view it both ways. But anyway, that was the second hand rule. Okay. And then the third hand rule is going to be more for this deflecting idea that we just show with like deflecting charges and like applying a force on charges there. All right. So here's the idea. Our fingers will always point in the direction of the external magnetic field. So they're always going to point from north to south. Okay. Our thumb is going to point in the direction of the particle's motion. All right, so our thumb's going to point in the direction of the particle's motion. So you can see this hand here, right? So if the particle is moving this way, that's kind of almost a bad picture because your hand should be like, your thumb should be 90 degrees to your fingers. You can't really see that from this picture. It should almost be more like this, right? Like the thumb part of that. And then finally, your palm is going to be the force. So it's going to be like a hand slap. Like your palm is the thing that's actually like doing like the force here. I'll show you an example here to make more sense. So it says for the following diagram, what is the direction of the deflecting force? So we know from above that this particle is going to deflect somewhere. So do this with me. Nobody can see you. So what we're going to do, we're going to say, okay, so fingers are, well, first off, it's for an electron, right? So it's still going to be the same thing with the first hand and the second hand rule, where I'm going to use my left hand for a negative charge, my right hand for a positive charge. So that always stays the same. Okay, so it's an electron, so I'm using my left hand, and I'm going to point my fingers from north to south. All right, so do that right now. Fingers are pointing north to south. And then this particle is an X, right? So that means I'm looking at the back of like the arrow, right? So this thing's going into the page right now. So that means my thumb should be pointing into the page. And if you guys are all doing the same thing right now, what you should have is your palm should be pointing upward. So this particle would deflect upward. Okay, so yeah, that's the idea there. Now, next one. So it says B, it says an alpha particle. Okay, so an alpha particle, we're going to talk a lot more about alpha particles a lot later, but might as well do it now. An alpha particle, all that is actually a helium nucleus. So what I mean by that, so if we had 2 neutrons and 2 protons, right? That's actually what helium is. It has 2 protons, like a charge of 2. And typically it also has 2 electrons orbiting around the outside, right? For a stable helium nucleus. But an alpha particle, we just give it a special name. And it's a particle that no longer has the electron orbiting around the outside. So it's been ionized. It's been like stripped of its electrons. So I can look at this and say, okay, well, this thing is positively charged. That's all I need to know for this question, is that there's 2 protons and no electrons. This thing has a positive charge on it. Okay, so what's going to happen here? So knowing that this thing's positive, all that changes, I'm going to use my right hand now, right? So north to south. So north to south for your fingers. Thumb is pointing into the page. Your palm should be pointing down. Okay, moving on. Okay, magnitude of the deflecting force. All right, so we have a new equation. So the magnetic force is going to be equal to the charge of the particle times the velocity that it was going times the magnetic field, and then times sine theta. And the sine theta part won't always come up. That won't always be an issue for us. What that is that if you've got a charged particle, let's say like an electron, and it's moving between, some magnetic field here, then what can happen is this charged particle can come in on an angle, right? And if it comes in on an angle, all we have to do is we're going to have to deal with our angle part of it. But for the most part, if this particle is coming in a straight line, so perpendicular to the magnetic field, right? Perpendicular, then the angle there would be 90 degrees, right? So, and then sine of 90 degrees, well, that's just 1. So our formula actually would simplify to this, right? And this means the force of the magnetic field is equal to the charged particle, or the charge of the particle, times the velocity, times, and then that's perpendicular magnetic field, right? Which just means 90 degrees for your angle.
If it was coming in on an angle, like what what angle would we use? Like an angle from the normal or an angle from like one of the magnets?
From the normal. And tell you the truth, for our purposes, it's never gonna like try to confuse you. It'll be the angle that shows up in the question.
Okay.
It's not going to be like, tell you the truth, it doesn't even come up that much in the questions that we do. The odd one will, but it'll tell you exactly the angle. It's not going to try to be tricky about it, and you know, like some of the other units we've done.
Okay.
Yeah, good question. Okay, okay, so that's the idea there. Now, oh yeah, sorry, I missed one. Particles in magnetic fields. All right, so here is what's going to happen, right? Is that, let's say that we have this negatively charged particle right here, right? So first off, let's actually apply our hand rule for a second. So I'm using my left hand, and I can see that it's moving to the right. So where it's moving, right, the speed of the thing is my thumb. Okay, so my thumb is pointing to the right. These X's, what I'm looking at right here is this is the magnetic field. I'm actually looking at the magnetic field, and these magnetic field lines are all going into the page, right? So like the magnets, it's kind of like a spatial thing here, but the magnets are like oriented the other way this time. And so what this means is my fingers will now be pointing into the page. So I'm using my left hand, my thumb is pointing that way, my fingers are into the page. You can see that at this point right here, right, there should be a force downward, right? So there's a force downward. So what that's going to do is cause this thing to turn, right? It's going to turn and turn and turn. And then if it turns all the way to this point, then if you think about it at this point, right there, well, my thumb would be pointing down now. My fingers are still into the board, and the force is toward the center. And you've got the same thing at this point where your thumb's pointing that way, and now the force is going to be pointing upward. This really reminds me of something from Physics 20. This is circular motion, right? We have one constant force directed toward the center of the circle. That's Fc, right? That's giving me a centripetal force. And that Fc, I know what that Fc is. There's only one force going on there. Fc is equal to Fm, right? That our Fc is equal to our magnetic force. That's going to be useful. We can do things with that because we can say, okay, well, if we know that Fm is equal to Fc, then with our new formula, QVB is equal to mv squared over r, right? That's just what Fc is equal to. Now we could actually figure out what the radius was. As long as we knew what the mass of that particle was, we can figure out how much this thing would bend. Or, right, if we knew the radius, we could figure out what and how fast it was going. We could figure out what the mass was, right? Like we can start to figure out what some of these quantities are using this idea, right? Okay, so that's like piece number one. We're gonna be kind of piecing a few things together here. Now, yeah, velocity selectors. So what a velocity selector is it's a device that's used to, well, actually here, I'll piece it all together in a minute. So a velocity selector really is just a device that's used to actually figure out what a velocity is going to be on a given particle coming through. And here's what I mean. So if we had, in this case, some positive particle, right? So let's use our hand rules again. So we've got this positive particle, and I've got a few things going on here. Like it's getting a little bit confusing, but can you guys see that right here? It shows B is into the page. So that's what they're saying. They're saying that the magnetic force, the magnetic force, so FB or FM, it's called a lot of times, is into the page. Okay, so let's just think about that one for a second. Just ignore these like plates that are going on there right now. So I'm using my right hand, and the particle is moving, moving to the right. So my thumb is to the right. My fingers are into the page. You guys are probably like a little twisted up right now. That kind of happens. So you should see that your palm would be pointing upward. So we have a magnetic force pointing upward right now. Okay, so magnetic force pointing upward. Okay, so just we have that one kind of figured out in our minds now. And then if I ignore the magnetic field now and just focus in on the plates that are going on there, right? Well, those plates, if we think back to last unit, right? These are electrically charged plates, right? This is This is just a, positively charged plate and a negatively charged plate. And I can just imagine when this thing comes in, it's positively charged. Okay, well, this positively charged thing, that's going to be attracted to that negatively charged thing. And it's going to be repelled from that positively charged thing. So this thing is going to be pushing downward, right? So the magnetic force is pushing upward and the electric force is pushing downward. And why this is a velocity selector is because the scientists can actually just tweak the dials on these things, right? They can give, some more charge on the plates or some less charge on the plates or some more magnetic field or some less magnetic field, right? They can tweak the dials to make it so that these two forces are perfectly balanced. Okay, so if those two forces are perfectly balanced up and down, well, the net result would be this charged particle traveling straight through and out the other side. If they weren't balanced, what would happen is that the particle would come here and it would bend and like hit the wall on the other side. It wouldn't come out the hole on the end, right? So we know that if this particle comes through the hole on the other side, that these two forces are balanced. That's the idea, right? So if those two forces are balanced, we can do something with that, right? So the whole point of that was that once I know those particles are coming out the other side, now I can do this equation, right? Because now I can say that Fe is equal to Fb, right? Our forces are equal. And what that allows me to do is I can say, okay, well, let's say I know what the charge is and I know what the electric field strength is, and charge again there, and I know what the magnetic field strength is because I set the experiment up, right? So I know those things. And then what you can do is the charges would cancel and we would just get the equation V is equal to the electric field strength over the magnetic field strength. So we can actually figure out how fast that particle was going based on just those two things that we set up in our experiment, right? Those are all things we can control. This is going to be important because it's actually like for scientists, they need to figure out how fast, let's say, particles, are moving when you have like radioactive decay. They need to know that, right? Like what, for one thing, whether or not that radiation can be harmful to you, right? Like they can learn different things from that speed. Okay, and another thing they can learn from that speed is this, right? So we're kind of piecing this all together now. So a mass spectrometer is our third piece here. A mass spectrometer is actually just putting these two ideas together. We're going to take our velocity selector, right, which helped us figure out velocity, and we're going to combine that with particles in a magnetic field, right? It's just we're putting them together is essentially all we're doing for a mass spectrometer. And here's the idea. So we've got three parts. We've got an ion source and an accelerator. So what this could be, some ion source, right? This could be radioactive material that's like giving off charged particles every once in a while. It's shooting these particles out, right? So it's gonna shoot these particles this way. And then what this is, well, this is just our velocity selector. That's the same thing that same picture we had above. So why they do this? Well, here for a second, let's start over here. Let's say if I said, okay, FC is equal to FM, right? So if I'm looking at this one, right? Well, what we're looking at here, those dots going into the page, that's our magnetic field, right? So let's think about that for a second. So let's say that this thing was negatively charged. So negatively charged particle coming right here, right? And it's moving this way. Okay, well, my fingers are into the board. Oh, sorry, they're coming out. This is positively charged. Okay, never mind. Let's say it's a proton or some positively charged particle. So these dots, they're like the heads of the arrow. So they're coming out of the board, right? They're out of your page. So your fingers are coming out of the page and your thumb is pointing this way, right? Your palm should be pointing down, right? So that's what's causing this circular motion here, right? So what we can figure out from that though is the radius, right? We can figure out what the radius of this circle was based on the path that it took. Okay, well, let's say FC is equal to, oh, sorry, I did that. MV squared over R is equal to, and then FM was equal to QVB. So just QVB, right? This is really just from up here. So that's just really this equation, right? Okay, so why this is important is because, well, if I want to figure out the mass of this guy, right? So what I could rearrange this really quickly and say the mass is equal to QVB over R, and then over V squared, I guess, right? And then that would cancel with one of those. So we get the mass is equal to QVB over R times V. Okay, great. So I could figure out what the mass of some particle was just based on how much of a radius this circle had. But I don't know the velocity of it, right? I know the magnetic field. Let's say I know the charge because I set up the experiment here, right? I knew what ion I was dealing with. And I know the radius. I'm just missing the velocity, right? That's the only thing. Like I could just do this experiment and I could figure out the mass if I only knew the velocity. Okay, well, maybe you're seeing where I'm going here. That's why we need the velocity selector. So the velocity selector, just what we did up in this one above, right? On this one, we can figure out the velocity and then we're good to go. So once we know the velocity, then we can just plug that into this equation. Okay, so I know there's a lot of parts here, but let's kind of go through each one. So
Again, how did you, shouldn't the R go to the top on the other side?
oh shoot, thank you. Did that really quick. Okay, yeah, you are correct. So M would be equal to Q RB over V in the end. Yeah, thanks. But yeah, either way, right? So yeah, now we know that we need to know the velocity, and then we're good to go because we know the radius, we know the charge, we know the magnetic field strength. Thanks, though. Yeah. Okay, so our velocity selector would be just this, right? So your step number one, if you've got a question like this, would be to figure out what the speed of your particle was, because we're going to need that for the second part, right? So just setting it up as FE is equal to FB. I find that's usually the hardest thing for kids to like just start with, right? As soon as they like write that down, they're usually kind of good to fill it in, right? Like work their way down like we've been doing. But it's just knowing that process, that the only way this thing is actually getting through is if you've got your forces equally balanced out, where your FB is equal to your FE, right? And yeah, just watch out for that too, because sometimes it's labeled FB and sometimes it's labeled FM. So either one. Okay, so doing that, then we can figure out our velocity. And then the second part is this picture, right? That we know that the force, so FC, right? You have your centripetal force there. Well, that FC is really FM, right? That is, here I should write FM or FB, whatever. So then you'd say FC is equal to FM, and that's how you'd start that part of it. Okay, and then filling in our equations for each, and then you can solve for the mass. Okay, so this is a huge part, like of well, we're going to talk a lot more about it in another unit when we get into like nuclear physics and stuff too, and more quantum mechanics and stuff. But yeah, so here is an example of the type of question that you would get. So let's say you've got uranium-235 and uranium-239. It's just like two questions in one here, but let's just focus on 235 for a second. And it says each has a charge of +2, okay? And they're directed into a velocity selector, which has a magnetic field, and we know the magnetic field, and we know the electric field strength. So we know B, and we know E. And so step number one would be to figure out, okay, the charge of this thing. So a charge of +2 means it has 2 extra protons, right? Or it lost 2 electrons, right? So in the end, it'd be 2 times 1.6 times 10 to the negative 19 coulombs. So that number, right? 3.2 times 10 to the negative 19. All right, now, since each proton and neutron has the same mass, right? So you guys, hopefully from chemistry, remember that, and it's on your formula sheet too, so you don't have to memorize it, but the mass of a proton and the mass of a neutron are essentially the same. So what we can do is just say, okay, well, if uranium-235, and when it's written like this, like uranium-235, that's what it's referring to. It's referring to the atomic mass of the particle when it writes like that. So that would be your atomic mass on your periodic table. So what that means is we've got 235 times our mass of a proton or a neutron, because I don't care. They're both the same, right? So I don't have to figure out neutrons and protons. I can just multiply it by the same number. So there is my mass of my particle. Okay. And then here's what we were talking about before. So then we'd set up our velocity selector. Fe is equal to Fb. Work our way down like we did above, and we'd get a velocity of 5 times 10 to the 7 meters per second. Okay, now that we have that velocity, we can use that in the ion separator, right? And that's the curved part. That's the one that curves, where it, gives us our radius. So Fm is equal to Fc. Work our way down, solve for R. So we end up with R is equal to, on this one, they just asked for the radius. Yeah, they weren't looking for the mass. Yeah, because we already knew it. So in this one then, we just set it up as R is equal to that. And then really the only difference between uranium-235 and uranium-239 in the question is that that'll change your mass, right? That's the only one that's different. All your other numbers are the same for this one. Okay. Van Allen radiation belt. There's quite a bit in this lesson, by the way, just to let you know. So Van Allen radiation belt. So the Van Allen radiation belt is, well, our Earth, the Earth, I should say. Let's say it has a North Pole and a South Pole. But technically that's wrong, isn't it? If we're talking magnetics, then let's draw it the way it should be, south and north. Because it actually is backwards, right? Like on our Earth, it's our North Pole is actually a magnetic south. But anyway, so what we have, since we have our magnetic field, right? Then we'd have a magnetic field that's being directed like this around the Earth, right? So you have those field lines that we talked about before. Okay, so part number 2 of this is that we've got our sun, right? So here's our sun, and it is constantly spitting particles at us, right? There's radiation, cosmic radiation coming at us at all times. And this can be lots of different things, but a lot of it is charged particles. So what'll happen, you get, like, let's say this positively charged particle that's moving very fast toward this magnetic field. Well, okay, well, that's everything we were just talking about above, right? So it's moving toward this magnetic field. What's going to happen is this thing is going to be deflected. And what happens is that they get deflected up, and they will usually all be channeled down toward the North and the South Pole, right? And this is our northern lights, right? That's Aurora Borealis. That's what's happening there, is that we've got all these charged particles are interacting with our atmosphere because they're colliding with our atmosphere mostly at the poles, right? They're not really colliding much with our atmosphere down here because the magnetic field is taking it and channeling it up toward the poles. So yeah, I always find that kind of neat. That's what the northern lights really are. And we talked about in our light unit why that would be, right? Those particles are interacting with different molecules, and light is just going to reflect off them different. It's going to produce different types of light because of that interaction of the particles, right? When they're striking the air molecules, or nitrogen or anything else, right? Okay, so that's our Van Allen radiation belt. And why it's a belt is because it's all kind of like collecting here, right? This is actually like a protector of our planet. This is actually this idea that we have this magnetic field that's putting out, that's like protecting us from this radiation. This is one of the things that makes Earth special, because Mars, they think, used to have this. It used to have a magnetic field because it used to have a hotter core. Like, they're still not exactly sure why, or like what makes our Earth have a magnetic field. That's still a big part of the research. But they do know it has something to do with being molten, right? Like, we have a molten core, like an iron core, and Mars has cooled off over time, and they don't have as much of a magnetic field. So what happened there is that Mars, let's say I'm looking at Mars now, let's say it doesn't have a magnetic field, or it has like a very weak one. Well, then now the surface of Mars is going to be just peppered with all this harmful radiation that's going to strip it of all of its life. So yeah, and that's essentially what happened to Mars. They think that's one of the theories that happened to Mars. But it used to have, like, they're thinking it used to have water, and maybe it used to have life and everything else, but just lost its magnetic field. which was so catastrophic for it. So yeah, we should be happy we have a Van Allen radiation belt that protects us. Okay, black and white television. Okay, so black and white television. So I always find this kind of neat. So if you're looking at this is like the screen of our television, right? Then what they had, they don't really work this way anymore with LED technology and everything else, right? But what it originally was that there was a phosphorus screen, and the way a phosphorus screen works is that you would see like a white layer on it. Like once there was like these electrons are gonna like run into the screen, it's gonna glow for a second, and then when they leave, it'll dim. So what they were able to do with that phosphorus screen is that they would take a magnetic coil, right, and an electron gun, so shooting electrons this way, and they would make the magnet like different. They'd change the magnetic field in this thing constantly, that it would like shoot up there and then shoot down there and then shoot down there, just based on the principles we were looking at above, right? So what that would do is they could actually move those things around in such a way as to make a picture on the screen. So it's actually just all happening in this magnetic coil to actually give you a picture on the screen, which I find amazing. It just doesn't seem like that would work to me, but they obviously made it work. Okay, practice problems. Okay, so for the following diagram, what is the direction of the deflecting force that the particle is a proton? Okay, so proton, using my right hand, it's going into the page. So my thumb is pointing into the page. My fingers are going from north to south. So they're going to the left there, right? So this thing would be deflected. Your palm should be pushing up. Your palm should be pushing up there. Electrons on it. But yeah, so it's going to be a negatively charged one. So now just left hand, everything the same, north to south. So now this one's going to be going down, right? Okay. Positively charged. So going into the page here. So positively charged, I'm using my right hand. And sorry, it's coming out of the page. So you should have your thumb pointing to the right, your fingers coming towards your face, and then your palm should be pointing down. So your force would be down, right? So what that would do if you had the downward force is it would make this thing start to do a circle. And if it didn't have anything on the bottom, it would actually just keep going around and around in the circle. So that'd be your path, yeah. Okay, this one, you know what? I think you guys will be fine. This one's just straight up putting it into our formula. So we've just got our Fm is equal to QVB sine theta, right? Just make sure that you put this in as 7.5 times 10 to the negative 6 coulombs, right, for your micro coulombs. And then, yeah, that should be good. All right. So we'll end it there.